Dear Kadria community, my name is Lin Meng from the University of New South Wales and an embedded researcher at HDR Inc. On behalf of my co-authors, I'm presenting t-SNE, a dimensionality reduction tool for design data realization. Many have stated that the data is the new oil. This is also true for the architecture, engineering, and construction industry. Over the past decade, we have observed the exponential growth of design data enabled by computer-aided technologies. And we also observed the tendency of AEC industry to leverage the design data to support the decision-making process. More data analytical tools are introduced to the AEC. In the year of 2020, machine learning comprises an important part of these tools. However, it is pointed out that the current design data realization process are often limited by the way the data is managed and displayed. The image on the left-hand side shows a typical object-oriented BIM model that attributes are sorted under each of the building elements, as is proposed by Zumora in 2011. The design data should have multiple views that presents the data simultaneously and consistently to help the users to search for correlations for diverse types of attributes. Therefore, one could ask the question, how can we intuitively observe the increasing complex information of the buildings, while compress the various high-dimensional design data into low dimensions in order to assist the design decision-making process? We will start with a case study of HDR Inc.'s data-driven master planning project as the background of the experiments, and move on to the proposed methodology, introducing t-SNE and ISOVIST as the key method of extracting geometrical information and processing high-dimensional data. Results of two experimental projects will be shown and discussed. And finally, we will provide conclusions and suggestions for future works. Information stored in a building model can be extracted and converted into various formats. This GIF shows the extraction of pairwise room relationships by measuring the shortest path in the model. In the same fashion, two different hypothetical layouts of the same campus are proposed and processed as dataset. The data was converted and displayed in a data dashboard to inform the design decision-making process. Data from this project was further used in experiment 2. The paper presents two experiments using t-SNE in architectural projects. A machine learning-based method was proposed by Peng et al. In 2017 in classifying the architectural space types. The method extracted spatial data using ISOVIST and classified them using convolutional neural networks. Experiment 1 adapted a similar method, but instead of using supervised convolutional neural networks, we used unsupervised t-SNE and made observations from the clustered data points. For experiment 2, we reused the dataset created in previous mentioned case study, including pairwise room relationships established by the trip path, and room attributes such as building name, faculty name, and room functions. To be more specific, I will go through the key concepts of t-SNE and ISOVIST. t-SNE is a dimensionality reduction algorithm created by Meaton and Hinton in 2008. It can be seen as an improved version of stochastic neighboring embedding algorithm. The letter T in t-SNE stands for the student T distribution, which is reflected in the scaling of the pairwise similarity. Introducing the t-distribution scaling helps to smooth out the extreme dense and extreme sparse data clusters in high dimensions. Input data of t-SNE can be considered as unlabeled data points, comprising values as high-dimensional vectors. As indicated on the left-hand side pseudocode from the original paper, the process of operating t-SNE involves the following steps. First, it calculates the dataset's pairwise similarity P between each point in high dimension, and calculates its corresponding low-dimensional projection Q. Second, the cost function measures the Kullback-Leibler divergence C between Q and P, which is a measure of the difference between two probability distributions. The cost is minimized iteratively using stochastic gradient descent, a typical machine learning optimization technique. In this way, data points are clustered in the lower dimensional representations over time. t-SNE was widely recognized in reducing data dimensionality for data visualization. For example, Bell used the convolutional neural networks to create a high-dimensional embedding of product images, and used t-SNE to cluster them to cluster with the similar graphical meanings. ISOVIST measures the volume or areas of the space from a given point of the space. It is a well-known method in assessing spatial configurations. It also has numerous implementations in popular computational platforms such as Grasshopper and Dynamo. In the context of this paper, ISOVIST is used to collect a distance array from the geometrical centroid to the first obstruction measured at the equal distance. We use Orange 3 for t-SNE clustering. Orange is an open-source machine learning and data visualization library implemented on Python, and it is also a visual programming platform for day-to-day data mining tasks. The Project 1 was based on the real-world architectural BIM model of an education building. Datasets include features of function, departments, room names, and its ISOVIST vectors. t-SNE was performed purely based on ISOVIST data, and plots was colored to verify its effectiveness of clustering. From the first run, on the left-hand side, we can see the data points forms many meaningful clusters. We need to note that the red dots are labeled with base build, which indicates that the room is out of the project design scope, rather than having a different purpose in design. On the right-hand side, we can see the chill-out zones forms a distinctive cluster, while 30 people learning studio can be barely distinguished from double 30 people learning studios. This fits the geometrical observation of these rooms, that 30 people learning studios are similar, while the chill-out zones are distinctively different. Project 2 uses the dataset from HDR case study. Features of the data include pairwise trip distances, faculty names, building names, room functions, room Cartesian coordinates. The same t-SNE plot was colored by different features, and it is clear that t-SNE performs the clustering well by being able to distinguish each individual features. At the beginning of this paper, we asked the question, how can we leverage this data even further to inform the decision making? By experimenting with t-SNE, we have explored new ways to present design data that could be more intuitive and truthful. Through the work of the two projects, we were able to demonstrate t-SNE presents high-dimensional data in low dimensions in a more intuitive way as graphical plot. What could be done by laboriously viewing several plans, tables, or 3D views in a BIM model can be potentially integrated in one flat graph. t-SNE equally consider all input attributes. From experiment 2, we observed that all features are taken into consideration as expected. Being able to preserve high-dimensional neighboring relationship means t-SNE may reveal hidden information observed from lower dimensions. As is indicated in Project 1, cluster with two mixed labels indicates that input data are similar. The algorithm discovered a hidden piece of information that was not explicitly labeled, that those two types of rooms are actually in the same design. Moreover, as an unsupervised learning technique, t-SNE is less intense in data preparation. Being implemented on several platforms and multiple programming languages means that t-SNE is easily accessible by a broader range of users. Even though t-SNE is powerful in clustering data points, like any information graph, the conclusions is dependent on the personal interpretation. Without prior knowledge of the data source, t-SNE cannot guarantee the conclusion has practical value to the projects. Project 1 and Project 2 suggest that t-SNE can be more useful in combination with other data mining processing techniques. Similarly, t-SNE may also be limited by a poor source of data, messy dataset, or lack of data interpretability. t-SNE cannot read Revit files or industrial foundation class files directly. The algorithms itself has certain limitations as well. t-SNE performs a stochastic process, which may generate slightly different results each time. Comparing with PCA, the iterative process of t-SNE has made it computationally expensive. Therefore, we position the future works in the following areas. Study the difference between t-SNE and other unsupervised learning models. Further investigate how t-SNE may inform the design decision-making process by applying t-SNE in a broader range of visualization tasks in architectural design. Find suitable data processing technique and workflows in architecture to ensure the meaningful plot can be achieved with the least amount of computational resources. Apply t-SNE in combination with other machine learning techniques to further leverage the abundance of data in the AEC world. We can further predict the designer user cases for t-SNE. It can find and suggest design elements with similar features without looking into the details. It can present design data in an all-in-one graph. It can cross-validate datasets that might have missing entries by discovering the features or relationships that are not explicitly established. Therefore, we should conclude that through the exercise of applying t-SNE in the design data visualization process, we have gained understanding of how much machine learning technique may help architects to leverage the value of data in the age of digital. This work was carried out as embedded research at HDR Inc. in Sydney, Australia. The lead author wishes to thank Australian Government Research Training Program, the sponsorship of HDR Architecture Scholarship, and intellectual contributions from the following people and group: Garth Hyland, Graham Spencer, Matthew Goldsberry, Scott Floro, Stefano Cotini, and HDR D3 Group. The presentation is over. Thank you for your attention.